Alright, we're going to talk about lesson 6.3, so please go ahead and make a new page of notes and update your table of contents. It's 6.3, adding and subtracting radicals. We're also going to be talking about how to do some familiar operations when the radicals we're working with are being added or subtracted to something else. Before we can get started adding and subtracting radicals, though, we have to know what radical-like terms are. Radical-like terms work very similarly to how variable-like terms work, and a lot of other like terms that we're already familiar with. But for radicals specifically, like terms have to have the same index and also the same radicand in order to be considered like terms. Now this is very similar to variables. In order for us to have like variables, let's go ahead and compare that on the side here. In order to have like variables, our variables have to have a few things in common. They have to have the same letter. So x's can only be combined with other x's, that sort of thing. And they have to have the same exponent. So I can only add x squareds to other x squareds. I can only add x's to other x's. So we're going to see some examples of like radicals next to some examples of like variables, and I think we'll be able to draw some similarities here. So let's take a look at like variables first. Like variables have the same letter and same exponent. So I could have a variable x, and I could add it to a 2x or a 5x. They both just have x inside, and that x is to the first power. So those are all considered like terms. For radicals, they work the same way as long as my radicals have the same index and the same radicand. So if I have the cube root of 7, I can add that to any other radical that also has the cube root of 7. So 2 times the cube root of 7 would be considered a like term because I have two things called the cube root of 7. And I can do 5 times the cube root of 7 as well. These are all considered like terms because just like my variables, they have the same number inside and the same number on the outside. So the same index and the same radicand. So in this situation, both of my sets of examples, the first one I've just got one of my terms, so 1x, one thing called the cube root of 7. The next one I just have two of these like terms, and the last one I have 5. The radicals can be more complicated as well. It doesn't change our situation at all. So if I have, for example, the square root of 6xy, I can combine that with any other radical that also has the square root of 6xy. So like 9 times the square root of 6xy. That would be considered a like term because I have the same second root and the same 6 and x and y inside my radical. We do have a note to keep in mind at the bottom here. When adding and subtracting, indices and radicands will never change. Indices is the plural of the word index. So I'm going to write indexes off to the side, even though it's improper, just so you know what indices mean. So indexes, plural indexes, are called indices. So when we're adding and subtracting, the indices that we have and the radicands that we have will never change. The only way to change my index or my radicand is through multiplication or division. I can't do it just by adding and subtracting. So let's go ahead and actually take a look at some examples of adding and subtracting radicals like these. We're going to start with adding. So we're going to take a look at a general form of adding any radicals. So let's say I have the radical n roots of x. And let's say I have a number of these. I don't know how many, let's just call it a. So I have a certain number of the radical called n roots of x. And I'd like to go ahead and add more. So let's say in this group I have b things called n roots of x. In order to add these together, just like I would with any other like terms, I would just add together the counting numbers in front. So if I have a over here and b over there, if I add them together, I'll end up with a plus b as my final number. So if I have like terms, then all I have to do is add the coefficients. So, for example, if I have 2 times the cube root of 4, and I have 3 times the cube root of 4, I have 2 things called the cube root of 4. I have 3 things called the cube root of 4. If I add them together, I'll write the long form here. All I have to do is add the 2 and the 3 from the front to find out how many cube roots of 4 I have after I add them, which in this case, 2 plus 3 would be 5. So we just add the coefficients in the front. Subtracting works exactly the same way. So if I have a nth roots of x and I want to subtract b nth roots of x, all I have to do is subtract the a and the b from the front, just the coefficients. So an example of that would be, let's say I have 5 roots of 7x, so 5 square roots of 7x, and I want to subtract the root of 7x. In this scenario, I have 5 things called the square root of x, and I want to take away this one thing called the square root of x. It has an invisible coefficient of 1. So all I would have to do is subtract the coefficients. If I've got 5 of these, I'm taking away one of them, I would end up with 4 square roots of 7x left over. So we just subtract the coefficients. Now, sometimes we have to simplify a radical before we can find what the like terms are. So we're going to go ahead and take a look right at something like that. So this is simplify radicals, if necessary, to find like terms, and this will be example A. In example A, we will have the cube root of 250. We'll have to add the cube root of 54, and then we'll have to subtract the cube root of 16. And if you'll notice, none of these seem to be like terms, because even though they have the same index 3, none of them have the same radicand. But once we simplify these radicals, we might find that that's a little bit different. So let's go ahead and simplify these. I'm going to start with the 250, and I'm going to break it up into pieces. In order to bring anything out of this radical, I have to have a set of 3. So we're going to break the 250 into pieces until we see 3 of the same number inside. 250 is 25 times 10. And I have to keep breaking these into pieces. 25 is 5 times 5, and 10 is 5 times 2. And now that I've broken it up, I can see that I have 3 5s. So I can bring a 5 out of this radical. The cube root will stay the same, and the only number left inside is the number 2. Let's go ahead and try the next one. In the next one, we have the number 54. That's 9 times 6. I will have to keep breaking them. 9 is 3 times 3, and 6 is 3 times 2. And again, I have 3 3's. So my 3 can come to the front of my radical. 3. And then the cube root is the same, and the only number I have left inside is the number 2. Interesting. All right, we've got one more to look at here. We'll take the 16, break it up into pieces. It's 4 times 4. We can keep breaking these into pieces as well. 4 is 2 times 2, and this is also 2 times 2. And now we only need a group of 3, so I'm going to take 3 of these 2's, and I can move one of them to the front. And the other one will be left inside my radical. That 2 right there. Now that I've finished simplifying, if we take another look at the radicals that we have in front of us, all of our radicals have the cube root of the number 2. All of those radicals have the same index and the same radicand now, which means they are like terms, and I can go ahead and actually combine them. All I have to do in order to do that is just to combine these coefficients out front. I have a 5 plus 3 and a minus 2. That will be the new coefficient of my radical. So 5 of them, add another 3 of them, and then take 2 of them away. We can actually do that math. 5 plus 3 is 8, subtract 2, I have 6 left over. 6 things called the cube root of 2. That is a 2. Let's try that again. Nope, still an eraser. Okay, here we go. So that would be our final answer. Let's take a look at one more example of that. We're going to simplify our radicals to find our like terms. So we have 6 times the square root of 20, and we're going to subtract 3 times the square root of 125. Now our index is invisible. It's just the number 2. So we have like indices, but we don't have like radicands. So let's see if we can simplify these to find the radicands inside. 20 is 5 times 4. 4 is 2 times 2, and since this is the second root, I need a pair to bring something out of my radical. The 2 will move to the front. Now we already had a number in the front. We had the number 6, and that number will stay the same. It will just stay out in front with the 2, and they'll just get multiplied together. Inside the radical, all I have left is this 5 right here, so times the square root of 5. Up next, let's take a look at this number 125. We'll break this into pieces. 125 is 5 times 25, and 25 can be broken up into 5 times 5. And again, we only need 2 of something to bring it out of the radical, so I have a pair of 5s. We'll go ahead and bring that 5 to the front, and we'll multiply it by the 3 that I already had. And again, the only thing left inside my square root now is going to be this extra 5 right here. Now that we've done that, we can see that our radicals are indeed like terms. I have the same index 2, and now I also have the same radicand, which is just the number 5. All I have to do is actually simplify the coefficients out in front. 2 times 6, that's 12, so I have 12 square roots of 5 over here, and I need to subtract 5 times 3, which is 15 square roots of 5. If I have 12 of something and subtract 15 of that thing, I end up with negative 3 square root of 5, and that problem is all finished. Now we do have a couple more things to talk about, because now that we know how to add and subtract radicals, we can work with expressions that have radicals being added and subtracted inside of them, and we can do more things with them. So the next thing we're going to talk about is how to multiply binomial radical expressions. Binomial radical expressions means I have a radical that's being added or subtracted to a number, and I'm going to do work with that entire binomial. And multiplying these will require us to know how to combine with multiplication, which we learned in the last couple of days, and how to combine with addition, which we just learned how to do. So it's important that we know the difference between multiplying, where we would have to combine our radicals and combine the numbers, the radicands inside, and addition, where we only combine the coefficients on the outside. So let's go ahead and take a look at an example of this. In this example, we are going to have 3 plus 2 square root of 5. We can only combine and add terms if they both have radicals, and they don't, so the 3 can't combine at all with the 2 and the root of 5. They're not like terms. We're going to take this binomial and we're going to multiply it by 2 plus 4 root 5. Again, another binomial that can't be combined, and I want to multiply these together. Now we already know the technique for multiplying binomials, and that hasn't changed. We're going to have to FOIL these if we want to combine them. So let's go ahead and take a look at that process. To FOIL these, we'll have to multiply the first terms first. I'm going to write it out the long way to show you how we can combine these. So 3 times 2. I'm just going to write 3 times 2. Then we have to do our outside terms, 3 and 4 root 5. So we're going to add 3 times 4 root 5. Up next, we'll do the inside terms, 2 root 5 and 2. So we'll add 2 times 2 root 5. And then we'll do our last terms, which are 2 times the square root of 5 times 4 times the square root of 5. Now we've done our FOIL process, first, outside, inside, and last. Now we'll actually go ahead and combine everything we are able to combine inside these terms. 3 times 2, piece of cake, we can do that. That's just the number 6. Up next, we have 3 times 4 times the square root of 5. We can only combine the square root of 5 with another radical that has the same index, and we don't have any other radicals in this term, which means the only things I can combine here will be the coefficients and the constant. So 4 things called the square root of 5. I'm going to multiply that by 3. We'll multiply the 4 by the 3. We'll end up with 12 things called the square root of 5. Up next, the same thing. I have 2 times 2 times the square root of 5. I can't combine the square root of 5 with anything. All I can do is multiply the coefficients out front. 4 things called the square root of 5. Up last, we have something interesting happening. In purple at the end, we have 2 radicals and 2 coefficients. I can still multiply the coefficients together like I did before. 4 times 2 is 8. But this time I can also multiply my radicals. I have the square root of 5 times the square root of 5. I'm going to go ahead and start using the shortcut when we see that happen, okay? So the square root of 5 times itself. The square root of 5 times itself. We're squaring the square root of 5. If I square something that's being square rooted, all I'm doing is undoing the square root operation. So when I do the square root of 5 times itself, it just becomes the number 5. The square root of 5 times itself is the number 5. So that comes from those two right there. All right. All we have to do now is finish combining our like terms. And now that we've simplified our radical, we have the number 6 in front and 8 times 5 in back. 8 times 5 is 40. 40 plus the 6 in front is 46. In the middle, I have 12 things called the square root of 5 and another 4 things called the square root of 5, which gives me a grand total of 16 things called the square root of 5. And that would be our final answer for this problem. Let's go ahead and take a look at one more example of this process. In this example, we're going to have 5 plus, the square root of 3. And we're going to multiply that by 4 minus the square root of 3. There we go. And again, we're going to FOIL this together. This time I'm going to go straight to my simplifying step. So 4 times 5, that's my first terms, that's 20. On the outside, we have 5 times the negative square root of 3, which is negative 5 times the square root of 3. They're not both inside radicals, so I can't actually combine them. I just put them side by side. For my inside terms, I have the square root of 3 times 4, which is a 4 square root of 3. That one was both positive. And up last, I have the square root of 3 times itself, one positive, one negative. So negative square root of 3 times a positive square root of 3. Now again, I'm multiplying the square root of something by itself. That square root will cancel, and that just equals the number 3. So let's go ahead and combine some like terms. We'll start by combining the terms in the middle. We have negative 5 things called the square root of 3, and I'm adding 4 things called the square root of 3. We just have to combine the coefficients. Negative 5 plus 4 is negative 1 thing called the square root of 3. I'm just going to write the negative square root of 3. The 1 doesn't have to be in there. All we do now is simplify my constants. 20 minus 3, that's 17, minus the square root of 3, and that's my final answer. We've got one last thing to talk about in this video, and that's how to rationalize a denominator if my denominator is not only a radical, but if it's a binomial radical, because the process has to change just a little bit. What we'll notice in this coming situation and the one we just looked at is this actually draws a lot of parallels to multiplying complex numbers. When we multiply complex numbers, which if you remember are imaginary numbers and real numbers combined together, when we multiply complex numbers, especially binomials, all of my i's tend to simplify back into real numbers when I multiply them together. And when I multiply complex binomials, I end up with a binomial as an answer. And the same kind of thing is going to happen with these radicals. When I multiply a square root of something by itself, it's going to simplify back into being a rational number, and I'm going to be able to simplify this into another binomial. The same kind of thing is going to happen when we have to rationalize a binomial denominator. It's going to draw a lot of parallels to our complex numbers unit. So hopefully when I show you how to simplify this binomial denominator, it should come back to you faster because you've seen something similar to this before. In order to rationalize a binomial denominator, we are going to have to multiply the top and bottom by the conjugate. We've talked about the word conjugate before, and I'm going to go ahead and show you again what it is. A conjugate has all of the same numbers as a regular binomial, but the sign in the middle has been changed to the opposite sign. So if I had a plus sign in the middle, it'll change to a negative. If I had a negative in the middle, it'll change to a plus. Let's go ahead and see an example of this. Let's say I have the equation 4x over 3 minus the square root of 6. In this denominator, I have a radical, and I'm not allowed to have a radical in the denominator. But if I try to use our old technique of just multiplying the top and bottom by that radical, when I multiply the denominator by the square root of 6, it will get rid of this radical, but it'll also distribute a square root of 6 to this number 3, and I'll still end up with a square root of 6 in my denominator. It's not going to go away. So instead of doing that, I have to multiply by the conjugate. And again, the conjugate has all the same numbers, 3 and the square root of 6, but the sign between them, this minus sign, will change to a plus. It'll just be the opposite. And we'll multiply that on bottom, and we'll multiply that on top. 3 and the square root of 6, but the sign between them will be a plus. All we have to do is distribute this, and my radicals in the denominator will cancel and disappear. So in the numerator, we'll distribute my 4x to the 3 and the square root of 6. 4x times 3 will be 12x. And if I take 4x and multiply it by the radical of 6, that radical doesn't have any other radicals to combine with, so the 4x will just have to be next to it. There's no way to actually combine those. All right, now when we look at the denominator, we're going to go ahead and have to FOIL these together. So let's go ahead and look at FOILing these together. Our first terms, 3 times 3, that's going to be 9. Our outside terms, 3 times positive root 6, is just going to be 3 times positive root 6. There's really nothing I can simplify there because I only have one radical. And again, when I do my inside terms, negative root 6 times positive 3 is negative 3 root 6. I can't really combine them, but hopefully now we'll see why these are going to start canceling each other out. My last thing that I have to do is multiply this negative root 6 by this positive root 6. Negative times a positive is a negative, and a root 6 times a root 6, like we talked about before, that radical will cancel. Let's go ahead and finish simplifying this. The numerator has nothing to combine. I can't actually add those x's because this one on the right has a radical in it, and I can only add things with radicals if they have matching radicals in the other term. So this 4x root 6 is stuck by itself. In the denominator, we've got a lot of stuff happening. So let's go ahead and look at this guy first. Root 6 times itself. Like I said before, that's the square root of 6 being squared. The square and the square root will cancel, and it just equals the number 6. So this number is just the number 6, which means I have 9 over here, and I have 6 over here being subtracted. So this is just going to be the number 3. And in the middle, I have a positive 3 root 6 and a negative 3 root 6. They have the same radical with the same index and the same radicand, the square root of the number 6. So we just add the coefficients, positive 3 minus 3. They cancel. They're gone. And I have nothing left in the denominator except the number 3. So this guy right here would be my final answer. All I had to do to get that final answer was just to find the conjugate, which has the same the same number in front, the same radical with the same index and the same radicand, but the only thing that changed was the sign in the middle from a negative to a positive, and we did that on top and bottom, and we were done.